Right? So most of you know these two equations for mass balance. dm by dt, mass flow rate at inlet, mass flow rate at outlet are same. Right? So under steady state, steady flow condition, we can write number 1, number 2. Number 2 is energy balance. Energy balance tells you d over d time is equivalent to P dot 1, P dot 2, and from there we learn here M1 and M2 are same. That's why I am using this equation in our tutorial question. Q dot T over dt. W dot T M dot
Reagan.
mass M dot alright. So today's tutorial I am using two equations. One is this and one is this. Okay? And in the class I explained you how we can derive this equation. One is mass balance, one is energy balance. So this one, the energy brings by the fluid at inlet and at outlet, and this is the heat and work interaction at the outlet, heat and work interaction at the inlet. That's all. Okay, heat and work that enters into the system, heat and work that goes out from the system, right? And this is the fluid brings that amount of energy at the outlet, and this amount of energy the fluid brings at the inlet. Okay?
I thought the energy balance should be E2 minus E1.
Same, E2 minus 1 is equivalent to 0. Under steady state. Steady flow means rate of change. Rate of change of energy. This one is 0. Then I can write E prime 1, E dot 2. Okay, this is the concept. Steady state. For transient, okay, not undergrad course. It's complicated. So now, the question. You take the pictures, that easy.
Hard to see. Can let me take a picture? I go home and email it.
Yeah.
Thank you.
Okay.
All right. So next one, the question. This is related to steam turbine. Steam flows steadily through an adiabatic turbine, as shown in this figure 1. The inlet condition of the steam are 6 megapascal, 400 degree Celsius, and 80 meter per second. And exit condition are 40 kilopascal, 92% quality, and 50 meter per second. The mass flow rate of the steam is 20 kilogram per second. Determine the change in kinetic energy, the power output, and turbine inlet area. Alright? So what is the inlet condition? State 1 is, this is the state 1, right? I write here 1, I write here 2, 1 and 2 outlet. And inlet condition is 6 megapascal and 400 degree. So I can easily find H1 and V1, right? With respect to 6 megapascal and 400 degree Celsius. We can get one. Alright. Now, state 2. State 2 is 40 kilopascal and 0.92% quality. So then I can easily calculate H2, V2, I can easily calculate, no problem. Okay, and the mass flow rate is given, m dot is 20 kilogram per second. That means mass flow rate at inlet is 20 kilogram per second, at outlet also 20 kilogram per second. Okay, and they also tell you the velocity at inlet is 80 meter per second. The velocity V1 is 80 meter per second, and V2 at outlet is 50 meter per second. Okay, first question is change in kinetic energy. I think solve it easily, right? What is the change in kinetic energy? V2 square minus V1 square by 2, right? This is the change in kinetic energy. So V2 I know, V1 I know, and I can get it. No problem, right? So question 1 is easy for us. Number 1 is change in kinetic energy. Change in kinetic energy is equivalent to half V2 square minus V1 square, right? So I know all the numbers. I put them, I get the answer. So question number B, the power output. That means W dot out, I have to find. And C, turbine inlet area. At that portion, what is the area? A1. Correct? Then how we can find W dot out? By the energy balance. Energy balance tells me what is this number. So B, I can get it from energy balance. I show you later. B W dot out, you can get from energy balance. This is the concept, right? And what is the C? How you can find the turbine inlet area? You remember what is the mass flow rate? What is the mass? Volume by specific volume. Remember, total volume by specific volume. So what is the mass flow rate? This is the volumetric flow rate by specific volume. Correct? So specific volume at inlet and total volumetric flow rate at inlet. So what is the total volumetric flow rate? Area times velocity by specific volume at state 1. This is the mass flow rate. Correct? This is the basic equation. I can write from here, very simple. So this value is 20 kilogram per second. This value I have to find. Velocity is 80 meter per second. V1 I get from the steam table with respect to 6 megapascal and 400 degrees Celsius. We substitute all the value, then I can calculate A1. Done. Okay? So this is the concept, how to calculate A1. Q1.
So that was one number.
Hmm?
M dot equal to V
A1 times velocity V1.
V1.
V. V indicates the velocity, and this indicates small v is specific volume at state 1. Done. Okay?
Small v.
These are the concepts I can find. Not difficult question. So now what I can do? I show you, right? Very simple. What? This is the change in kinetic energy. Change in kinetic energy. Right? I can write V2 square by 2, V1 square by 2, 50 square by 2, 80 square by 2. So this is joule per kilogram, 1.95 kilojoule per kilogram. This is the change in kinetic energy. And what is the power output? This is the basic equation. Q dot in, W dot in, M dot 1, H1, V1 square by 2, ZZ1, Q dot out, W dot out, M dot 2, H2, V2 square by 2, ZZ2, right? So this one is cancelled, this one is cancelled, change in potential energy is cancelled, Q dot out is 0 because of adiabatic. Then W dot out becomes M dot H1 minus H2, V1 square by 2 minus V2 square by 2, right? Done. So this is the basic equation I can write. So W output is change in enthalpy and change in kinetic energy. Done. So now I am going to substitute the value and get the result. So can I go next slide?
Yes.
No problem, is it? Now you can see the table. What is the table one? 6 megapascal means 600 kilopascal and temperature is 500. Am I right?
Yeah.
Temperature is 500 or 400?
400.
400. So this is the specific volume you want. And this indicates H1. Alright?
Yeah.
3178. So I can write V1 and H1. From table A5, P2 is 40 kilopascal, right? With 92% quality.
Yeah.
This one is HF. This is HF, right? 317 point something. HF and HFG I can get. Oh, this is missing actually. Some number you can get from the table, which is HFG 32318.4. This is HFG you can get from the table. Then we substitute the value, we can get H2 and this is H1. Then V1 I also know. Now I am going to substitute the number. Then I can find W output is equivalent to 14.6 megawatt. So this is change in enthalpy, change in kinetic energy. This indicates a change in enthalpy, change in kinetic energy. This is for unit balance. 1 by 1000 for unit balance. Then you plug in this value, then you can get the answer. Alright? And the turbine inlet area I show you. This is the specific volume. I am going to find this number. So I substitute the number. This is the mass flow rate. This indicates the specific volume at state 1. This is the velocity at state 1. And this is the area, which is 0.0119 meters square. Okay? Not difficult actually. If you understand the concept, it's easy. You can, if you know the mass flow rate, mass times volumetric flow rate is A times P. So P I know, so A I can easily find. Just substitute the values. Okay. So now I can go to question number 2. As shown in figure 2, this is the figure 2. Steam enters a D superheater. This indicates a D superheater. operating under steady state condition. This is a steady state condition at 30 bars and 320 degrees Celsius. You understand? That means here fluid enters into a desuperator. This is a chamber, right? Adiabatic chamber. No heat is lost from this chamber to the outside. In the push chain it is mentioned. Alright. So this amount of fluid enters into the system. You can write what amount of fluid? 30 bar. 30 bar means 3 megapascal, right? 3 megapascal with 320 degrees Celsius. This amount of fluid enters into the system with the mass flow rate of 50,000 kilogram per hour. Okay. And another fluid with the pressure of 2.5 megapascal and temperature is 200 degrees Celsius. This is the compressed liquid fluid. This is the superheated fluid. This is the superheated fluid, and this is the compressed liquid fluid. This is the compressed liquid fluid enters into a desuperheater. So we assume here the mass flow rate is m.1 and here is m.2, the mass flow rate, right? Then enters into a desuperheater, and here saturated vapor is generated, right? And from this outlet, the superheated vapor goes to another system. So this is superheated vapor, this is compressed liquid, this is saturated vapor. So I can say 2 inlet and 1 outlet. So outlet is pink color I put here. So mass flow rate is m.3 and condition here is 2 megapascal, right? 2 megapascal, 20 bar is 2 megapascal with saturated vapor. Saturated vapor condition. Alright? And they tell you what is the mass flow rate at state 2. You have to find out the mass flow rate at state 2. Okay, so how you can solve the question? And they also mentioned that no heat is transferred from the device to the surrounding. That means from here to surrounding is 0. Q out is 0. So this is the control volume, correct? This is the control volume. And what we can write? dm by dt is equivalent to m.1 plus m.2 minus m.3. What I can write? I can write this is dm, right? dm by dt. What happens here? So dm by dt is equivalent to how much fluid enters into the system? m.1
M1,
m.1 plus
M2,
m.2. And how much fluid is leaving from the system? m.3.
minus
Right. For steady state, steady flow condition, dm by dt is equivalent to 0. Because we assume the total amount of fluid in that system is fixed. Doesn't change for every time. Okay. So that's why I can write m.1 plus m.2 is equivalent to m.3. So what I can write? The mass balance tells me m.1 plus m.2 is equivalent to m.3. So this is one equation. So from mass balance I know m.1 plus m.2 is equivalent to m.3. What is the inlet condition? 1, 3 megapascal and 320 degrees Celsius. At state 2, pressure is 2.5 megapascal and temperature is 200 degrees Celsius, compressed liquid. And state 3, 2 megapascal, saturated vapor phase. That's all. Okay? So now I am going to do energy balance.
All the steps tell me.
Alright? So mass balance tells me. So this is m.1,
I don't need to do what?
m.2. Mass balance tells me m.3 becomes m.1 plus m.2. So what is the energy balance? I show you how to write. Take a look. Energy balance is Q dot in plus W dot in M dot 1 H1 V1 square by 2 GZ1 plus M dot 2 H2
plus GZ1
GZ2 is equivalent to Q dot out plus W dot out
plus
M dot 3 is 3 C3 square by 2 GZ3. In that question, we assume number 1, there is no change in kinetic energy. Is given. There is no change in potential energy. 0, right? And is there any Q input externally? No, right?
No.
There is no heat output, right? There is no work interaction. Right, this is a small chamber. Yeah. It doesn't produce any.
What if it is a big chamber?
This chamber.
What if it is a big chamber?
If it is a big chamber, same thing. Because
Same thing,
this is an insulation chamber, and here the fluid enters into the chamber, they mix together, and vapor is generated. Very simple. Here, fluid brings energy only.
So no difference.
There is no external heat source, right? And the system doesn't losses any heat. So that's why you have to understand this. Otherwise, you cannot solve the question. Then I can say this is 0, this is 0, right? 0, 0. Bye bye, right? No. All bye.
Wow.
Then I can write.
M1 H1
Very good.
plus M2
M dot 1 H1 plus M dot 2
H2
H2 M dot 3 H3, right? Then I can write. Can I write now? M dot 1 H1 M dot 2 H2, this one. M dot 1 H3 M dot 2 H3. I can write, right? Because M3 becomes M dot plus 1 plus M dot 2. Then after that I can say M dot 2 becomes M dot 1 times H1 minus H3 divided by H P minus H2. Alright? Then M dot 1 is given 50,000 kilogram per hour. Then H1 I have to get from the table. H2, 3 I can get from the concept. And H2 I can get from here. Right? From the steam table I can get it. Then, now you understand, right? So what is the value of H1? Tell me. H1 becomes Hg with respect to 3 megapascal and 320 degrees Celsius. So what is H2? Compressed liquid, right? This is compressed liquid. Then I can write HF with respect to 200 degrees Celsius. And what is H3? Hg, saturated vapor with respect to 2 megapascal. Done. Then you calculate all the value from the table and put it here. Then you get the answer. Okay? And the concept is not very difficult. I hope you can solve it. So now I am going to show you the table. Okay? State 1, 3 megapascal and temperature 320. You do not have, right? Then you have to find from the interpolation. That means I can show you H1 minus 2994, right? H. 2994.3.
Calculator no use, is it?
P is 116.1 minus 2994.3 is equivalent to temperature, right? 320 minus 300, 350 minus 300, right? Then you can get H1. H1 is equivalent to
你为什么要做assignment？你有关那个 calculator？
3043.02 kilojoule per kilogram. Right, done. I show you here, right? Why I show you here? In the quiz, many people do not do so far. Okay? I show you here again. So do more practice. So H1 I get it. What is H2? H2 becomes at 200, right? This is H. That means 852.26 H2. What is H3? Hg with respect to 3 megapascal or 300,000 kilopascal, which is this value. Now this is HL. This is Hg. 2803.2. Okay? So now you have to substitute the number, then you can get the answer. So you can take this data, okay? Alright. Okay, what is the mass flow rate of liquid? So you can get it easily, right? M dot 2 becomes M dot 1 times H1 minus H3 divided by H3 minus H2. M dot 1 is given, right? 50,000.
Huh?
50,000 kilogram per hour. This one 3043.02 minus 2798.3. What I get from the table is 2798.3 minus 852.26, right? Then you can get under 2. I get here 6287.64. This is kilogram per hour, right? So if I tell you calculate M.2 in terms of kilogram per second, what do you do? M.2
Times 60 times 60.
7.64 divided by 60 times 60, right?
Wow.
This is kilogram per second. All right. This is the answer. Very straightforward.
So the correct answer is wrong.
This one is old table. People use the old table.
This is 264 is wrong.
This is 1960 water table.
Then why you got 1960 answer?
This is a textbook answer.
Okay.
They use the old steam table. This is the new or latest steam table. Because I give you the steam table, right? You use it. Okay? And the error is very negligible. This is now.
Hey, the school print shop still open?
The school?
Close. What time close? I
Okay.
thought forever one.
Now is the last question.
Ah, yeah. Later I need to print something.
This question, not easy. You have to understand.
Got color or not? The difference?
This question you have to understand. Otherwise, you cannot solve it.
Oh, maybe, yeah.
This is a complicated question.
Exam is more complicated or easier?
Exam should be complicated.
More complicated than this, than question 3. More complicated than question 3. Or this one?
Similar to like this. Okay, take a look. Air as an ideal gas. This is the air as an ideal gas. At steady state, through the compressor and the heat exchanger, as shown in this figure 3, data for various flow stream are given in this figure. All these point delta given. Heat loss from the both systems to the surrounding are not considered. That means Q dot out from the compressor and Q dot out from the heat exchanger. Okay, assume there are no changes in kinetic and potential energy. That means change in kinetic energy 0, change in potential energy also 0. Alright, they tell you calculate the compressor power in kilowatts. So this value is what you have to calculate, and the mass flow rate of the cooling water. Here is the cooling water. Okay, you have to find. So in that question, take a look. Air with the pressure of 96 kilopascal at 27 degrees Celsius with the volumetric flow rate of 26.91 meter cube per minute. Right? So this amount of fluid enters into the compressor. Right? After compression, the air temperature increases up to 127 degrees Celsius and pressure also increased from 96 kilopascal to 263 kilopascal. This is the outlet of the compressor. Later, the pressurized and high pressurized and high temperature fluid or air enters into the heat exchanger. Correct? In the heat exchanger, we supply water, right? What happens? Water absorbs that amount of heat. Correct? And water outlet temperature increases from 25 to 40 degrees Celsius. And pressure of water drops from 2 bar to 1.5 bar. So we remember this is the compressed liquid. And the outlet of air temperature drops from 127 to 77 degrees Celsius. And pressure is same pressure. Because air is flowing through this, right? And air rejects heat to water. And they tell you how much power is needed to run the compressor, W dot in, and what is the flow rate of water. Right? And the volumetric flow rate of air is given. So I can easily calculate the mass flow rate of air, right?
Yeah.
How? This one you do not know. How to calculate the mass flow rate? So this is the state 1. I write here, this is state 1, this is state 2, this is state 3. Okay? This is state 4. And this one state 5. How many states? 5 states. How many process?
2.
No? 3 process. 1 to 2, air compression. 2 to 3, heat rejection. 4 to 5, heat absorption by water. Okay? 2 to 3, heat rejection by air. 4 to 5, heat absorption by water. Okay? So this is the understanding. Now I can solve easily. First one is my mass balance. Later I do energy balance. Correct? That's all. Not difficult. So what is the mass balance? Mass balance tells me, you see, for the air. For the air, I can say m dot 1, m dot 2, m dot 3, right? Same. Same, right? It's not difference. They are same. You can say this is equivalent to m dot here. M dot A, right? Is here. For the water, another mass balance. For the water, I can write m dot 4 is equivalent to m dot 5 is m dot water. And you have to find what is this number. You have to find this number, right? Okay. So after that, I do energy balance and mass balance. Okay. Mass balance, okay. First I do mass balance, I show you here. The energy balance I do from 1 to 2, then 2 to 3, then 4 to 5. That's all. Can I go next? Okay, what is the mass flow rate here? How to find? This is the ideal gas of air, right? What is the equation? PV equals to MRT, I know, right? What is M? PV by
Sigma.
RT. Correct. Any problem? No problem. So what is the mass flow rate? From here I can write m dot becomes PV dot by RT1, right? At inlet. M dot 1 becomes P1 V dot 1 RT1, right? I can get it, right? Easy. So what is the P1? 96 kilopascal. V dot 1 26.91 meter cube per minute. R 0.287 for air, which should be given to you. And T1 is 27 plus 273, 300 Kelvin. That's all. Understand? Now I am going to show you. Okay, first I show you the mass flow rate. Otherwise, we will memorize. M dot 1, I show you P1 volumetric flow rate at 1. This is the volumetric flow rate, right? By RT1 is equivalent to, what is P1? 96. V dot 1, 26.91. What is R? 0.287 kilojoule per kilogram Kelvin. And this one is 300 Kelvin, right? 27 plus 273. 300 is 27 plus 273. I show you here again. This one becomes 27 plus 273. And the answer I get here 30 kilogram per minute or 0.5, right? Kilogram per second. Am I right? 30 divided by 60 kilogram per second. Done. So what is the energy balance between 1 and 2? Tell me what I can write. I write the basic, right? Q dot in plus W dot in, right? So this is the M dot air, right? So this indicates M dot air. So M dot air times,
Wow.
don't worry, it's coming. M dot A, because I traced the cross sign, that's why it happens. So this one is H1, V1 square by 2, is at 1. Right, so this one is Q dot out plus W dot out M dot A, right? H2 this is at 2, right? Now what I can do? Q in 0. Very good. W in
0.
ah. Change in potential energy 0. Change in kinetic energy 0. So W dot out Q out 0. 0, right? So what you can write? You can write W dot in is equivalent to M dot H2 minus H1, correct? So W dot in M dot A I know, right? So H2, what is H2? H with respect to 127 Kelvin or 400 Kelvin. 127 degrees Celsius or 400 Kelvin, same. Minus what is H1? H with respect to 300 Kelvin. 27 degrees Celsius is 300. 127 is 400. Okay? That's why. And we get this data from the table. I show you later the table. Remember, we get the data from the given table. I will give you the table and you can get the data from the table. Get data from the table, right? Table A17. We will do.
A7.
Done. table is under Kelvin. Air, ideal gas, you should use absolute temperature, absolute pressure, right? Done, right? So now I am going to show you. Okay, this one energy balance between 1 to 2.
That's why you
Compression.
confident.
Air compression, right? Then you understand. 1 to 2 is air compression. I can get it. Can I go next?
Yes.
Okay, now I am going to show you energy balance between 2 to 3. What is happened here? 2 to 3 is here, right? This is the control body. Pink color. So 2 to 3, what we can write? Tell me. 2 to 3, between 2 to 3 is heat rejection, correct? In 2 to 3, what I can write? Tell me. I just follow the previous thing. Q dot in plus W dot in plus M dot air times H2 V2 square by 2 C is 2, right? Is equivalent to Q dot out M dot A H3 V3 square by 2 Z is 3. Correct. Now is the Q in is there? Yes or no? You look at the pink color. This guy gets any Q in from other? No, right? This is 0. W in is 0. It never produces any power. 0. Change in kinetic and potential energy according to the question check. So Q out is present or not?
Yes.
Yes, because this guy loses heat from here to surrounding. So Q out is present. Good. Now you slightly understand. Q in is 0. This one is 0. This is 0. By. Correct. Then I can write. I use it here pink color. So you can write. I can write. Q dot out becomes. What is Q dot out? Q dot out becomes M dot A H2 minus H3. Am I right? Good. So M dot A I know, right? This value I know. 0.5 kilogram per second. Okay, I know. What is H2? H with respect to 400 Kelvin, right? What is H3? H with respect to 77 degrees Celsius or 350 Kelvin. All right, 350 Kelvin. So I can write Q dot out. So I say this is Q dot out, right? So now I am going to write the energy balance between 4 and 5. Between 4 and 5, what I can write? Tell me. Q dot in, W dot in plus M dot water. Am I right? Yes, M dot water is H4, right? V4 square by 2 plus ZZ4 is equivalent to Q dot out, W dot out plus M dot water H5 V5 square by 2 ZZ5. So we assume change in kinetic and potential energy we can neglect. Right. Is there any Q in to the system? Yes, because if you look at that point, it get Q in from pink color, right? Q in is present. Q in is present, but W in is 0. H4 is present. H4 is present. Q out no. W out no, right? Then I can write Q in becomes m dot water H5 minus H4. What is H5? HF at 40 degrees Celsius, right? This is HF at 25 degrees Celsius, according to the question. So I can write Q dot in. What is m dot W? I have to find. I do not know. This is HF at 40 degrees Celsius. HF at 25 degrees Celsius. Right. So here we can see this guy gets this amount of energy. Q in. What we can see? This value and that value are same thing, right? Then I can write this one equivalent to this one. Correct. So what you can see from here, I can see Q dot out from air, right, is equivalent to Q dot in with water. Right. Then I can say m dot water times this value is equivalent to m dot air, this value. Correct. Now I can easily calculate m dot water because I know here everything. I know here everything from the table. Right? And the question is solved. All right. Can I go next? Okay. Properties of air, right? What is H1? Tell me. What is H1?
400.
H1, I just draw here. H1 becomes, tell me. H with respect to 300. Oh, 300 is equivalent to, this is 300, right? 300.19. This table will be given to you, don't worry. What is H2? H with respect to 400 Kelvin. What is 400? 400. 400.98. Correct. What is H3? H3 is?
350.
What is H3?
350.
Yes, 350. 3 fourths H at 350 Kelvin. 350.49 kilojoule per kilogram. Then what is HF? H5? From the table I can get it, right? From another table I can get it. From the compressed liquid table. Then this is the table and this is HF. This value. 25 is inlet. Is this value. So what is H4? HF with respect to 25 degrees Celsius, which is 104.83 kilojoule per kilogram. H5, HF with respect to 40 degrees Celsius, 167.53. Okay? Then you can get from the table. You know this table. And the previous table, A17. Yeah, you can get from there. So now, we can write, right? You remember this one, right? M dot water times, right? H5 minus H4, you remember? m dot air times H2 minus H3. Correct?
Yes.
And turbine power you can get, I show you the turbine also. I show you the first, because I have the data. M dot W, what is M dot air? 0.5 times 400.98 minus 350.49 divided by H5 is 167.53 and this one is 104.83. Then I can find m dot water is 0.403 kilogram per second. This is the answer. Answer B, this one. And what is the turbine power? Remember? Turbine power is W dot in. You remember, right? Mass flow rate of air times H with respect to 400 Kelvin. H with respect to 300 Kelvin. Now we are going to substitute the number 0.5 times 400.98 300.19. Then I get 50.4 kilowatt. Alright, I give you the answer so you can. The most important thing is the understanding.
Also one second answer.
This one you take? You can take the picture also if you want.
So you
This is the last.
why the people count like different one? Yeah, different type.
This one you take, is it?
Oh, just suck ah. No need to put in water. Never see before, yeah?